Today we will look at another two differentiation techniques. They're the product and quotient rules. So far we have differentiated functions that have been added together or subtracted. So we might have looked at finding the derivative of something like this. And when we're doing that, it's fine to just go through and differentiate each term, adding or subtracting as it's stated. We cannot do that when the terms are multiplied or divided, and if we can look very quickly at a counterexample. If we've got an expression y equals 5x multiplied by x cubed, the easiest thing to do would be to actually multiply that together and simplify it as 5x to the power of 4, and then use our power law to differentiate it, so we'd get 20x cubed. If we look at going down that route of differentiating each part individually and then multiplying it, so if we differentiate 5x, we would get 5, and if we differentiate x cubed, we get 3x squared. We can see that we're getting a very different answer to the one above. So it's fine to go through differentiating terms when they're added or subtracted. When they're multiplied or divided, we need to use one of these two rules. So when we're looking at differentiating a product, we obviously use the product rule. And for this, we are going to look at the two things being multiplied together as u and v. U is a function of x and v is a function of x. So let's just take a look at that with this example. This first bracket is being multiplied by the second one. So I would think of this as u and this as v. And I'm going to apply the product rule. This is another rule that's provided to you in your formula guide. So I'm going to try and find du by dx and dv by dx first of all. So let me, just to make it really clear what's going on, I'm going to state what u is, and I'm going to state what v is. Okay, so I'm going to find du by dt. That's the variable that this is in terms of. So multiply by the power, reduce the power by 1, constant becomes 0. I'm going to find dv by dt. I'm going to do it using the chain rule. We talked last lesson about that shortcut where we think about multiplying the derivative of the inside function by the derivative of the outside function. So the derivative of the inside is -1. And I'm going to multiply it by the derivative of the outside function, which is raising to the power of 5. So multiply by the power, keep that, and I'm going to reduce the power by 1. If you're not happy with that approach, by all means use the formula guide, and you're going to be doing dy by du times du by dx. Okay, so now I've got all the elements all set out quite clearly here. I am ready to find ds by dt. Okay, because I'm thinking of s as u multiplied by v. So I'm going to do u, 2t squared plus 3, multiplied by dv by dt, -5, 4 minus t to the power of 4. Then I'm going to add v, 4 minus t to the power of 5, and I'm going to multiply it by 4t. There's lots of simplifying we could do. Really, it depends on what you're going to use this for next. I mean, I think it would probably be sensible just to tidy up by moving this -5 to the front, just so that we don't make a silly mistake like thinking that these are two separate terms that we're finding the difference of. And I'll move the 4t to the front of this just to ensure I don't make any errors moving from line to line in my work. At this stage it might be that you need to do a bit more rearranging if that's necessary in the question, but equally we could stop here. We have found the derivative. Multiplying all of this out, would have taken a lot of time, because we would have had to have, you know, multiplied 5 lots of this bracket together and with this. It would have been a lot of work. And this seems like quite a bit of work, but this would have been a lot more work as an alternative approach. This was not an example in your booklet, the next two are. So let's take a look at a couple of examples from your unit booklet. So this first one, we're using function notation. We've got a product here, so I'm going to have u, my first bracket, x squared plus 2x. I'm going to have v as my second. I'm going to change that 1 over x, I'm going to write it in index form, because it will make finding the derivative a little bit easier. So, finding derivatives, these are nice, straightforward things to be finding derivatives of. Negative x to the negative 2. Okay, so let's apply our product rule. So I'm going to do u dv by dx, x squared plus 2x multiplied by dv by dx. I think I'm going to go for writing this as 1 over x squared. I think that might make simplifying it a little bit easier. Next, we want v, which I'm going to switch back to 1 over x now, times du by dx. Okay, this looks like something that might be worth trying to simplify. I'm going to expand this first of all, which makes negative 1 minus 2 over x, and then I'll multiply out this. I would have 2 plus 2 over x plus 6x plus 6. Okay, those can cancel, and I'm left with 6x, and I've got 6, 2, negative 1 plus 7. Okay, this is an example of something that we should definitely not be using the product rule for, because this is actually far easier if we just multiply out the brackets. So I'm going to go back to this. Here's what we should have done. We should have multiplied out the brackets to begin with. X plus 3x squared plus 2 plus 6x. So let's just make that a bit tidier. And then we could have differentiated that really much more easily, and we get the same result. So the product rule is really useful, but it shouldn't be used every single time you have a product. Thinking back to that first thing we looked at, we shouldn't be using a product rule here, for example, and I'm sure we wouldn't dream of it. I'm sure we would go straight to simplifying. Same here. If it's easy to simplify, and we're talking really just 2 pairs of brackets, we shouldn't be using the product rule. This next one is a much better candidate for using the product rule, because really we've got 5 brackets multiplied together here, and multiplying all of that out is going to be a lot messier than doing the product rule, and you're more likely to make an error, an algebraic error. So this example is quite similar to the one we did before down here, so I think this might be one that we can skip, and you can use the uploaded solutions to check. So let's move on to the quotient rule. So we said adding and subtracting terms, that's fine. When we're finding derivatives, we just go through, find the derivative, add or subtract. If you've got a product, 2 things multiplied together, we need to use the product rule. If you've got things that have been divided, functions or terms have been divided, then we need to use the quotient rule. Once again, we talk about u and v. U is the numerator and v is the denominator. And as long as you can differentiate u and you can differentiate v, then you can apply the quotient rule. You can see the quotient rule is a little bit more challenging, or a little bit more complicated than the product rule. We can prove this using the product rule. So instead of thinking of it as u divided by v, if we think of it as u times v to the negative 1, and we then apply the quotient rule, the product rule to this, we can arrive at the quotient rule. This is not something you need to do. You're given the quotient rule in the formula guide, so this is really just a way of seeing one way of arriving at it. So if we're going to use the product rule here, dy by dx, we would start off with, let's find our product rule, u dv by dx. Well, u is just u, and then I need to multiply it by the derivative of this. So I'm going to need to use the chain rule. So I will get negative 1, I'm going to multiply by the power, I'm going to keep v, I'm going to reduce the power by 1, and I'm going to multiply, so that's the derivative of the outside. I need to multiply by the derivative of the inside as well. So that's my first term. So that's u, all of dv by dx. Then I've got v, my v is actually v to the power of negative 1 multiplied by du by dx. Okay, then we can simplify this a little bit. Okay, this v to the power of negative 2 I'm going to put down at the bottom of a fraction, and then this all becomes negative u dv by dx. Okay, this v to the power of negative 1 is going to go down to the bottom of my fraction, and I've got du by dx. This isn't quite what I want it to look like, so if I try and make some common denominators, u dv by dx, I'm going to multiply the top and the bottom of this fraction by v. v du by dx over v squared, and then I can combine this, and while I'm doing that I'm going to switch the order so that the negatives, we're not starting with a negative sign. v du by dx minus u dv by dx all over v squared. So that's one way of deriving our quotient rule from our product rule. One thing to note with the quotient rule is the order matters that you do these in now because of this negative. The product rule, it didn't really matter which way we did it. The quotient rule, we have to be a little bit more careful. So let's look at applying the quotient rule to this, this third example. So we're going to start by finding the derivative. As we were doing the product rule, let's set this all out nice and clearly. This is my u function, this is v. Can differentiate both of those, so we can use our quotient rule. That's 2x. Oh dear, I need to make sure my v's don't look too much like u's. That's just 1, and then let's find 2y by dx. So v du by dx, x plus 1 times 2x. You may feel comfortable just putting the 2x straight at the beginning, minus u dv by dx. Okay, timesing by 1. And that's all over v squared. Okay, I have found the derivative of this already. I'm going to need to use this a little bit, so I'm going to tidy this up a bit for us before we do that any more with it. So let's multiply that out. That is 2x squared plus, sorry, this tablet is lagging a little bit, plus 2x, and minus x squared minus 3. And then that will end up being x squared plus 2x minus 3, all divided by x plus 1, all squared. Okay, that's my derivative. Okay, so in part B we're going to find the tangent and normal at this point. This point is actually wrong, so the curve does not actually go through negative 2, 7, it goes through negative 2, negative 7. So let's just change that. So this is something we looked at last week, and you should remember that the tangent to the curve has the same slope as the curve at the point they meet. So when we're looking at the tangent, the slope of the curve will have the same slope as the tangent. So when x is -2, dy by dx is -2 squared plus 2 times -2 minus 3 over -2 plus 1 all squared, that's 1. So m is -3, and the point we're going through is -2, -7. So y equals m times x plus b. So we've got -6, -7 equals +6, sorry, plus b, so b will equal -13. So our tangent has the equation -3x minus 13. So from that we can also find our normal. Oops. Okay, normal. Well, if the slope of the tangent was -3, we know the slope of the normal will be +1/3, and we know it's also going to go through the same point, -2, -7. So y equals m x plus b, and this will be a little bit messier, -2/3 plus b. So b, I'm going to think of this as -21/3, so we would get -19/3. So the equation for my normal, y equals 1/3 x minus 19/3. Okay, before we finish, a couple of notes, tips to try and help you avoid making going down some routes that aren't always very helpful. The first is, it's generally best to avoid rearranging a quotient into a product rule. The product rule is simpler, but generally what you will get out of it will be less helpful than what you would get out of the quotient rule. And if you need to do something with that derivative, it's generally better if you stick with the quotient rule. The only time that isn't a case is when your quotient has a numerator that's just a constant, and then it is best to rearrange. And actually we're not even going to end up using the product rule, because this is just a constant. You don't have two functions being multiplied together here, so you could just use the chain rule. And that really is much quicker than going through the quotient rule, especially when you've just got this constant. So if you have a quotient with two functions, try and avoid rearranging for the product rule. If you have a quotient where there's only one function and then the other's a constant, the numerator's a constant, go for the chain rule.